opportunity to be here. I'm really enjoying myself. And so this is the first of two talks. Today I'm going to be covering mainly a lot of history, and in tomorrow's talk I'm going to be giving some more technical information about more recent results. So so this is a long paper. Oh, no, it says on. Maybe. Okay, sorry. So I'll speak louder. So this is a joint paper which I wrote with Alexander Itz and Igor Krasovsky. It appears on the archive. You can find it there. And it will appear in CPAM, and it's dedicated to Brewery Kaufman, and I'll explain why as we go along. This paper was a bit of an adventure for us. We made, as it were, the bold attempt to try and mix in some history of the Ising model, and we kept getting it wrong. I'm sure we still haven't got it completely wrong, but we spoke to many people, including Tom, and I don't know if we got it right in the end. We apologize if we didn't. But my main interest is really the following, is to see how the theory of Toeplitz matrices and Toeplitz determinants developed directly in response to a variety of questions which arose in the theory of the Ising model. So I'm not particularly emphasizing the history of the Ising model or the big, broad history of Toeplitz matrices, but I do want to just focus on the influence of the one on the other. Okay. Maybe I should bring this over. So what is a Toeplitz matrix? An n by n Toeplitz matrix. N by n has entries which are constant down the diagonal. A Toeplitz determinant is simply the determinant of such a matrix. A particular case of interest, of course, is if you're given a function which is integrable on the unit circle. The Toeplitz determinant, which is given by phi, is simply the determinant of the Toeplitz matrix you get by using, for your Cj's, the Fourier coefficient of the function psi. It's a simple exercise to show that if Cj equals minus Cj bar, then Tn is self-adjoint, and hence the eigenvalues lambda 1 and lambda 2 are real. This is true in particular if phi is a real function, then you get phi j equal to. Okay, so Toeplitz determinant matrices are named for Otto Toeplitz, who introduced them in his Habilitationsschrift in 1907. He was at Göttingen at the same time that Hilbert was developing his general theory of functional analysis. And Toeplitz had the idea of looking at these special examples of operators to illustrate Hilbert's general theory. Specifically, what Toeplitz was looking at, he was looking at quadratic forms where phi jk was of the form phi j minus k, and he introduced the notation of calling them L forms because of the connection via Fourier theory to Laurent series. Now, it became immediately clear that there were many applications of Toeplitz matrices. Here's a very striking one, which I like, and it has many applications, this particular one, to this day, which just illustrates just what a useful and unexpectedly applicable idea the notion of a Toeplitz matrix is. Here's a question purely in complex function theory. Suppose I give you a polynomial what properties should these coefficients have so that this function, this polynomial, has an extension which I call phi of z. So it's an extension to an analytic function in the unit disk. So d0 equals c0, d1 equals c1, and so what I'm doing is just adding on extra terms here in such a way that the real part of this analytic function is bigger or equal to 0 in the disk. Such a problem arises in many different cases. The answer, which was first of all given by Theodori in terms of some work of Minkowski, but the answer which Topelitz found is this very simple one. He says, such an extension is possible if and only if this Toeplitz matrix, which you build up out of the C's, and the C negatives are just the conjugate of this. If this matrix is positive definite, it's necessary and sufficient condition, suddenly this pure complex variable problem has its answer in terms of these Toeplitz. It's very striking. Now, there are many, many applications. If you want to see some classical applications, there's this book by Grenanda and Szegö, a famous book from the 50s or 60s. There are a whole set of papers by Fisher and Hartwig covering applications to analytic function theory, statistical, stochastic process, linear estimation theory, and statistical mechanics, and in particular for us, the Ising model, which we will get to. If you want to look at the early theory, there are a whole set of papers by Harold Woodham, by Botcha, Silverman, Grodsky, and they have the references there to earlier work of many, many different people. You can find that on the in our archive paper. I don't want to go into that. But the goal of these two talks is not to review the development and applications of Topelitz theory in a systematic way. I just want to look at one central problem. And the problem is the Szegö strong limit theorem, or SSLT. So what I'm going to do is I'm going to trace the history of this theorem and its later generalizations, simply in response to a succession of questions raised in the analysis of the Ising model. So the story begins in 1915 with Szegö. It was the very first paper that Szegö wrote. He was 18 years old, and he proved the following: that if phi is a positive and continuous function on the circle, then if you look at, did I leave off the n? Log d n phi over n is given by this formula. By the way, just in our long journey to try and write this paper, we found out many, many little pieces of information. Let me give you one sort of snippet, is that if you look at the early books, Szegö is written with 2 dots on it. Now that is, of course, the German umlaut, but the right umlaut you should be putting is the Hungarian umlaut, which has these 2 things. So somebody told me the following story, that in fact Knuth introduced the Hungarian umlaut specifically so that Szegö's name would be written correctly. So I tried to check the story out. I couldn't find a direct verification, so I decided to contact Knuth. And you can't just write him an email, right? He doesn't respond. So I had to write a longhand letter to him, inspired today's lecture, why I'm not using the computer. And I asked, is this story true? So he says it's only partially true. He says not only was there Szegö, there's Erdős, Koenig, and others. So that's the story. So Szegö immediately saw that if you express Dn in terms of the eigenvalues, then this is a special case of equidistribution in the sense of Weil for the eigenvalues. So then a few years later he proved the following result: if phi is a bounded function, bounded below by little m and capital M, and f is a continuous function on this interval, then as you can expect, you'll be able to prove the following theorem for equidistribution. The sum of the f of the lambda, the sum of the f of lambdas is given by that particular quantity. Now, if we remove the logarithms, we can rewrite the theorem, Szegö's initial theorem, in the following form, where the error term is little o n. The question, which is of great interest, is what is this term little o n? Can one estimate it? So now we begin shifting to the Ising model, particularly in two dimensions. I just remind everybody, I'm sure everybody here knows it, and so I'll say it very quickly. You've got spins, sigma ij, independent, plus or minus ones at site ij. The interaction energy is given in this form, nearest neighbor interaction, vertical and horizontal. We usually take the j as positive, so your system is ferromagnetic. You let lambda be a box of size n by n, and the interaction energy in the box is given by summing over all ij's in the box, and the convention is the boundary terms are included, or these ij's are such terms are included if either ij is in the box or ij plus 1 is in the box. So it's telling you that the top border and the right-hand border are included in the sum. You then introduce the Gibbs measure in the usual way, and you define the partition function also in the usual way. KB is Boltzmann's quantities of great interest, and in fact of principal interest are the correlation functions, which are the thermodynamic limit of the products of the spins at different sites. So A is just some fixed set in the lattice. We are particularly interested in the case where A just contains two points, sigma 1, 1 and sigma 1n, say. So it would be the correlation between the spin at 1 and the spin at n. So these objects are of great interest. So the key question was, does the Ising model, which Ising had introduced in the 1920s, does it have a phase transition? Now, what the well-known answer is that Ising showed that in one dimension there's no phase transition. In two or three dimensions, Ising thought that there's also no phase transition, but he was wrong. In 1936, Piles gave his famous argument showing that Ising exhibits spontaneous magnetization, two or three dimensions at some critical temperature Tc. As a little piece of snippet of information, it turns out that Piles' original argument was actually incomplete, and it was corrected in 1964 by Griffiths. I beg your pardon? Also, yeah. Was it the same time? Yeah. Yeah. Thank you. Now, the first question is, what is Tc? In a paper in 1941, Kramers in 1 year computed that in the case where the interaction coefficients are equal, Tc could be got by solving this equation. Then, in a famous story.
So was it Kramers and 1 year accepted Piles' argument?
Yeah.
I imagine.
Everybody
it's
did.
Not terribly wrong, maybe not quite
yeah.
perfect.
Incomplete. And if you look at Griffith's paper, in fact, Griffith credits Michael Fisher for pointing out that there was a gap. And then he showed it doesn't take much to correct it. And of course, the Piles argument remains a fundamental tool in all of statistical mechanics. Then, in a way which was very characteristic of Onsager's style, I believe. I wasn't alive at the point. But 1 year was giving a talk in 1942 at the New York Academy of Sciences, where he presented this formula. And then in a characteristic style, Onsager waited till the talk was over, and then he got up and said, actually, you can compute the entire partition function. And what he did was wrote down this answer over here. And what you can see that if you compute the specific heat, it's this quantity using this formula, you find it diverges logarithmically as T goes to the critical temperature, exactly the one which was given by Kramers and Wanier. And if J1 is not equal to J2, this formula is generalized to the following form. Well, in writing this paper, we heard about many stories about Onsager, some of which I may repeat. Okay. So in the mid-1940s, Brurier Kaufman, who was a graduate student at Columbia, decided that not only was she going to work on the Ising model, but she was going to work with Onsager, who was then at Yale. Now, this was a very brave thing to do because the Onsager's calculations were already by that point famously difficult and obtuse, and there was this young woman. She just wanted to work on it and with Onsager, and she eventually persuaded Onsager that she had a new way of looking at things, and by introducing Fermion methods, or specifically spinor analysis, she was able to give a new derivation of Onsager's partition function formula, or free energy formula that was a great simplification, even in Onsager's own words. But what Onsager realized is that the tools that Kaufman had introduced were much more powerful than what he had, and had the possibility of then being able to address issues like the spontaneous magnetization. And then in 1948, Onsager announced, again, Kaufman's methods played a critical role, that he and Kaufman had obtained a simple formula for the spontaneous magnetization. I think in all of physics there are a few formulae which are so beautiful and elegant, which answer such an important question. So this is the spontaneous magnetization, and this is for temperatures T less than Tc. Again, the announcement was done at Columbia, at Cornell in 1948, and again it was done in Onsager style, which means that people were saying, well, we now know how to compute the partition function, let's try and do more difficult things, like the spontaneous magnetization. It's very difficult, and then so Onsager waited until the end of the talk, and then he went up and he wrote down this form and says, this is the spontaneous magnetization.
What do you have inside the parentheses?
1 minus k, this quantity, squared to the power 1/8. So,
So how is it? Did they always treat the anisotropic case immediately?
Yeah, they did. Yeah, absolutely. There's a great way to find out what actually was going on, which I will mention later on. When say going on, what they were actually doing at the time. So when T is less than Tc, this number K on is less than 1. And when you're at critical temperature, of course, this quantity is equal to 1. They also showed that when T, well, they gave a formal argument that when T is bigger than Tc, the spontaneous magnetization, as you expect, should be 0, and the same would be true at the critical temperature. Now, here came the first real interesting twist in the story, is that Kaufman and Onsager never published a proof of their result. So we're going to say why that actually happened. What one can show, the spontaneous magnetization can be computed in terms of the two-point correlation function in this particular way. So you look at the correlation between spin 1, 1 and spin 1, 1 plus n, to the power of half and let n go to infinity. I must just say for the people who know, that's not the real physical quantity you would call the correlation function. I learnt a lot of this from Elliott's papers. There's a different definition, and there's actually a third one due to Yang, which I'll speak about. They all turn out to give exactly the same answer, but I don't want to focus on those physical. I'm just trying to keep the connection, as I say, between Ising and Topelitz. So what Kaufman and Onsager did publish in 1949 was the following. Let's put it under the name Ising meets Topelitz. So they showed that this quantity here, this two-point correlation, could be expressed in terms of Topelitz determinants. This is the beginning of the story. Take -1 to the end. You take this two-point correlation function. It's a sum of two Topelitz determinants, where C1 and C2 are constants, and phi1 and phi2 are symbols on these explicit symbols on the unit circle. So you immediately realize the following. So that in order to compute M0, the spontaneous magnetization, what they needed to do to be able to do was to compute the asymptotics of Topelitz determinants as n goes to infinity. So let me just show you that picture again. Here is the formula for M0. This object we now know is expressed in terms of Topelitz determinants. We need the asymptotics of that quantity. Okay. So they asked the mathematicians what was known about this problem, the asymptotics of Topelitz determinant. Now, all that was known, so we're speaking about late 1940s, or in fact a little before, was Szegö's original result, which was that d and phi was this quantity here, plus little o n, and as we said before, this is a term that you want to know. And also, as far as Ising, that is the term you want to know. So the question is, how did Kaufman and Onsager obtain their result for M0, and why did they never publish the proof? Firstly, they did not use this formula, which was one of the other features of Onsager's style. There was probably much more in his drawers than he ever published. He didn't use this actual formula. What they said, they used a formula which was not recorded in their 1949 paper, although it was known to other people like Cyril Dom and other people like that. Instead of looking at the correlation between 1, 1 and 1 plus n, in other words, between here and some horizontal point, they looked at the diagonal correlation between 1, 1, 1, and 1 plus n and 1 plus n. Again, you've got this physical argument which tells you that the spontaneous magnetization can be expressed in terms of such a diagonal correlation function. And the advantage now is that instead of this correlation function being expressed in terms of two Topelitz or a sum of, it's expressed in terms of one Topelitz determinant. And the form of the symbol just looks exactly like this. This k-ons was that quantity. We know k-ons is 1 if and only if you're at the critical temperature, and it's less than 1 if you're less than the critical temperature. Now, it happened like in all these very serendipitous things is that Onsager, as we know, was at Yale, and just a couple years before that, Wiener came to Yale, and he gave a talk on the Wiener-Hopf method, particularly in its application to Milne's equation in radiation theory. And then Onsager realized that that method could be adapted to compute this particular determinant. It would take me a lot of time to explain why, but if you know how to solve Milne's equation, you would see how to do. So you just apply it, and you see that this is going to come out. That's how they actually did it. Now, in the meantime, sensing that there was a much bigger fish to fry, Onsager and Kaufman began looking for a method to evaluate dt and phi for a general class of symbols. They only needed for this one, but they said, oh, there's a much bigger prize at hand. So they began looking for a general method. So it's very nice to actually...
What's the difference between the two cases, the horizontal case and the diagonal case? So they're both Toeplitz, right?
The original formula, I'll say more about it later, after the work of Potts and Montreal, is that in the original formula for the correlation along a horizontal axis, the two-point correlation function is expressed as a sum of Toeplitz determinants. On the diagonal, it's just a single, much simpler
Their sums, we're talking about a finite sum, or?
at the finite level. At the finite level.
Before you take that.
Yeah, before you take the limit. So Onsager and Kaufman are looking for a way to solve the general Toeplitz asymptotic formula. So he has a very nice quote from Onsager in his, he has some autobiographical writings from 1970. He says, and lo and behold, I found it. So he's looking for this general formula. It was a general formula for the evaluation of Toeplitz matrices. The only thing I did not know was how to fill out the holes in the mathematics and to show the epsilons, the deltas, and all of that, and the limiting process. I did not know just how it should be done and what mathematics mathematicians really knew about limiting processes in that ballpark. Now, as it turned out, by that point, mathematicians knew a lot. Was what had happened when they first found their Toeplitz representation. Onsager and Kaufman began speaking to mathematicians and asking what is known. In particular, they spoke to Kakutani, and then Kakutani spoke to Szegö, who then went back to his calculations from 1915 and eventually solved the problem of obtaining an expression for that little term, little on. So when they were faced with Szegö's general result, Kaufman and Onsager published, decided not to publish their computation. Now, the first method, which was just for this very specific symbol, nor the method which they had found for general symbols. Onsager has this nice quote. He says, the mathematicians got there first. Now, my view is a little bit like this. In the long history of mathematics and physics, it's most unusual for a physicist, chemist to be scooped out of a formula by a mathematician. Very unusual. So, one knows...
It was Szegö.
Beg pardon?
It was Szegö who first got the next step.
Yeah. No, actually, if you... So let me say, if you go to... There's a wonderful site, which is an archive for Onsager, which is maintained by the University of Trondheim. And there they have all the correspondence between Kaufman and Onsager. Actually, Kaufman was at the Institute for something like 8 years. She was the assistant to Einstein at the end of his life. Now, if you look in there, you'll see the whole correspondence between them. They actually, Onsager and Kaufman actually had the general formula, which appears in Szegö's work. So they really knew how to. But there's a real comedy of errors here, one of many comedies of error. And it goes like this. If you look at what Szegö had done, his method only applies to symbols which are positive, on the one hand. On the other hand, what Kaufman and Onsager needed was to work with a complex symbol, which I'll see. So the truth of the matter is that Szegö had not solved the problem. But at the same time, Kaufman and Onsager didn't realize that Szegö hadn't solved the problem. So it's, again, an example which illustrates that just as things happen now, people just don't read other people's work. So Szegö thought he had solved the problem, but he hadn't. And Kaufman and Onsager thought that they hadn't really solved the problem, but they had. So that's the way it goes. So what is Szegö's theorem? The strong Szegö limit theorem, and this is the one I want to concentrate on and show how it was further developed and generalized in response to further questions arising from the Ising model. So let phi be a positive function whose derivative is Holder continuous of order epsilon. Let log phi k be the Fourier coefficients of this quantity. And then you find that dn phi upon e to the n log phi converges to e to the e of phi, where e of phi is this particular quantity. So in other words, this quantity here, I'll just let you look at it for a moment, is the term little o n. Now, so this is the quantity over here that you need to plug in to be able to evaluate the two-point correlation function, if it also applied to the complex case, right? Yeah.
Can you show the formula for E once more, for E of phi?
Okay. Okay.
I don't understand. You're saying the next correction term, I forgot what it was. Is that small? The
Is
little
little o1. It's little o1.
In fact, little o1.
Yeah.
So we're both using this Wiener-Hopf method?
No.
Neither one.
No. Okay. Of course, in the special case, which I mentioned, that very special case, that's the first way that Onsager and Kaufman computed things. So there it was using the Wiener-Hopf. But the second method, the general method, does not. Ultimately, of course, everything is done by Riemann-Hilbert methods, and that's very closely related to. Okay. So there are many, many different proofs of the strong Szegö limit theorem. In his recent book on orthogonal polynomials on the unit circle, as Barry likes to call them, OPACs, Barry Sum describes 6 different proofs. In our archive paper, we describe 3 more. They're all very different and require slightly different assumptions on phi. Now, the ultimate result, sort of an if and only if result, was given in 1968 by Ibragimov and said, so let phi be a proper probability measure. This is a positive function on the unit circle, and suppose that log phi is integrable. Then the strong limit SSLT is true in the following sense. If you look at this ratio here, it always exists and always equals e to the e phi in the case where both one is finite and the other is finite, and the one is infinite and hence the other is infinite. So this is always equal to e to the e phi, even when this quantity e phi is infinite. So that's the answer. So let me I don't want to make this a focus of what I'm saying. So I just want to say a little bit sort of a mathematician's take on these things. So the mathematical challenge that is posed by this strong Szegö limit theorem can be viewed as follows. In functional analysis, one commonly considers continuous maps, F, say, from one fixed topological space to some other fixed topological space, Y. Then in order to verify that this limit is f of xn is equal to fx, all one has to do is to verify, of course, that xn goes to x as n goes to infinity in the topology of x. In particular, say if X is a space of trace class operators and a separable Hilbert space, and Fx is a determinant of 1 plus X, then F is a map from the trace class operators to the complex numbers, and limit of f of xn equals f of x if xn goes to x in the trace norm. But here you see what the difficulty is. The strong Szegö limit theorem is not of the standard functional analytic type. Instead, we have f from an n by n matrices to C, and if you take an to be some such matrix, f of an is the determinant of an. So the initial space x is varying with n. You're not in one of these fixed situations. And it's the underlying space is changing within. And it's not at all clear how to topologize the space of matrices so that f of an goes to limit of f of the limit. This is what the difficulty is. So what this really means that you've got to bring in some renormalization theory. Otherwise, you're not going to be able to do it. So all these different methods are just introducing one way or the other different kind of renormalization. That's what makes the problem have so many different kinds of solutions, because you can renormalize in different ways. Now, perhaps...
You know, Kate Kiola's work, she generalized it to higher dimensions.
Yeah.
Which is a quite different,
Yeah.
strong concept.
Yeah. Yeah.
She has a method which I think, I'm wondering which of your methods is the one she is using here.
Well, there's 9 to choose from.
Do you know?
Well, I don't
You
know.
haven't looked at that?
I certainly spoke to her, and I did definitely go, but I can't say I was thinking about that at the time. So perhaps the most elegant of these different renormalizations, very beautiful one due to Borodin and Okonkov from the year 2000, arose in the theory of random matrix theory and combinatorics. But what they showed was an explicit finite n expression, the determinant of a Toeplitz matrix. Now, after a renormalization by this log phi, this is zeroth Fourier coefficient, and you got this E phi in it. But then you change this Topelitz determinant into a Fredholm determinant. So K is some explicit trace class operator, and Qn here is the projection onto the Fourier or onto the components n plus 1, n plus 2, and so on. In other words, the projection onto the tail. So by general theory now, we know that as Qn's converge strongly to 0, Qnk, Qn will converge in the trace norm to 0. So we have converted, after renormalization theory, we've converted the problem into a renormalized standard form. So once you've got this formula, the strong Szegö limit theorem is immediate. Now, I just want to make a little technical remark, which is very important in applications, is that the formula is true at any fixed n. So they can incorporate into their point of view symbols which themselves depend on n. This is a very powerful thing to do, and there are a lot of problems which arise where you've got a n by n Toeplitz matrices, but your symbol itself is varying within. That can be handled very effectively by the Borodin and Okonkov. Now again, we've got this whole sort of comedy of errors running through the whole subject. It turns out that the formula of Borodin and Okonkov pact, in fact, was found by Case and Geronimo. That's Ken Case in 1979. But its importance and its utility were just not recognized at the time. Again, I think every day Harold Whittam wakes up and says, why didn't I read that paper? Okay. So that's the way it goes. Now, another proof, which is particularly appealing to physicists, is based on a Heine-type multi-integral representation. There's this beautiful formula which expresses a Toeplitz determinant in this particular way. So here's the symbol phi, and you get the e to the I theta j, e to the I phi k, and these are just points integrated over these circles. So this enables you to rewrite d and phi as a physicist would, which in terms of what one is called by Dyson a log gas or a Coulomb gas. And if you just do the algebra, it looks like that, where Hn is going to be given by this. Your symbol phi is e to the v, and w is this log interaction term. Now, immediately when you see this, you can say, well, you can say Dyson makes this very clear in his writings, is that this formulation immediately leads one to expect that the determinantal limit behaves like a thermodynamic limit, where there is a time on it and one well understood methodology of how to proceed. And Dyson, with incredible ingenuity, has solved many problems arising in the theory of Toeplitz terms by using such a formalism. But of course, it is an assumption that it behaves like a thermodynamic system. It's true, but that's not a proof. And to fill in the actual details requires a lot of work that was first done in this particular case by Johansen in 1988. So he made this thermodynamic type argument rigorous. Now, returning to the Ising model, we note that the strong Szegö limit remains true, as we've mentioned, even when phi is not real. All you need are two things: that phi should not vanish on the circle and that it has zero winding. In other words, you don't have to have just positivity. Then the theorem goes like this: if v is an L1 function with Fourier coefficient satisfying this condition, then the Szegö limit exists, but instead of given by k mod vk squared, it's k vk v minus k. So this is the theorem that you really want to use to evaluate the asymptotics of the two-point correlation function. Now, so what this means is that after the announcement in 1949 of the beautiful formula for the spontaneous magnetization, there was this result, but there was no proof. And Onsager and Kaufman didn't give one. And the first published proof of the formula was given by Yang. Now, I mentioned earlier on that the spontaneous magnetization in terms of this limit of correlation is not the real physical quantity. Well, Yang used a third representation, which is a priori different from the other two, from the real physical, but nevertheless, in the limit, they all give the same answer. And he used results from Kaufman and Onsager, but he didn't use Topelitz determinants explicitly. It's an extraordinary computation, and in his he's got some in his collected works. He comments on this paper, and he's got a very poetic description of his attempt to prove the Kaufman-Onsager formula, and I ask you to bear with me if I read it. It's such a poetic description. So it says, so this is Yang speaking. He says, I was thus led to a long calculation, the longest in my career. Full of local tactical tricks, the calculation proceeded by twists and turns. There were many obstructions. But always after a few days, a new trick was somehow found that pointed to a new path. The trouble was that I soon felt I was in a maze and not sure whether, in fact, after so many turns, I was anywhere nearer the goal than when I began. This kind of strategic overview was very depressing, and several times I almost gave up. But each time something drew me back, usually a new tactical trick that brightened the scene, even though only locally. Finally, after about 6 months of work off and on, all the pieces suddenly fitted together, producing miraculous cancellation, and was staring at the amazingly simple final result. It's very nice. Okay. So, in 1955, Potts and Ward made a very important technical advance. Now, remember we showed that if you looked at correlations along a horizontal, the correlation could be expressed in terms of a sum of two Toplitz determinants. That's different from what you saw along the diagonal. Nevertheless, Potts and Ward were able to show that, in fact, those two determinants, that some could be contracted into a single. It took them later on, I think, working together with Montrell to actually prove that the answer you got was the same as In other words, the one determinant form was the same as the sum of the two, but that's...
Which word is this? Is this the word of word identity?
I don't know. I can give you his... Okay. Which one is it? So it is Potts and Ward. It's J.C. Ward. That's the same one. Okay. So what they found was this. That the correlations along a horizontal line could be expressed in terms of single determinant where you have this particular symbol on the unit circle, gamma 1, gamma 2, gamma are expressed in terms of the fundamental parameters, J1 and T, in this particular way. Now what we need to see is that if gamma 1 will always be less than 1 and gamma 1 will always be less than gamma 2. The interesting thing is whether gamma 2 is less than 1, bigger than 1, or equal to 1. Gamma 2 is less than 1, it turns out, if and only if T is less than the critical temperature, bigger than 1 if T is bigger than, and so on. Now what that means is if you look at this object here, and suppose you're not at the critical temperature, so gamma 2 is not equal to 1, then each of the functions in here is nice and smooth on the circle, but when gamma 2 is less than 1, in other words, T is less than Tc, there will be no winding for this entire object here. But when you are bigger than 1, this will have winding. That will be the difference. So if you take T less than Tc, you'll find that this symbol here doesn't vanish and it has Z0 winding. So then the strong Szegö limit theorem applies. If you compute the Fourier coefficients log phi, you obtain these quantities here. You plug it into this quantity called E, and you come up with a nice sum, and that immediately reduces to the Onsager Kaufman formula. If you can do a similar computation, instead of going along the horizontal, you use the expression for the correlation along a diagonal. Instead of having phi Onsager, you have phi diagonal. It's a simpler computation, but you come up with the same answer. And it's immediately clear from here that as T goes up to Tc, this quantity K goes up to 1. And you expect it to be zero magnetization, and Onsager and Kaufman present a formal argument to this effect. Now, the issue now arises about the rate of decay. We know that when T equals Tc, this will have a limit which will be 0. In other words, there will be no magnetization. It became of great interest to know the actual rate. The first person to compute an actual rate was Michael Fisher, who made suitable approximations of the Onsager-Kaufman formula, and he obtained the n to the minus a quarter decay. Well-known result. Now, the first thing we begin to see, concentrating as we are on the relationship of these physical arguments to the SSLT, that if you look at phi diagonal, if you put T equal to Tc, your symbol takes this form. You put theta between 0 and 2 pi, and you see that there is winding. So the new challenge, so the first challenge that came out of Ising was to compute the magnetization for temperatures T less than Tc, and this whole Szegö machinery. Now we see a new challenge. We cannot just restrict ourselves to symbols which are smooth and of zero winding. We want to be able to know how to evaluate Toplitz determinants asymptotically when they have winding. That's the challenge, the next challenge which is brought. Similarly, for T bigger than Tc, we of course still expect the magnetization to be 0. And again, the question is to compute the rate of decay. Again, later on, in Michael Fisher computed the rate of decay. Here is at a site nm. K is the root of n squared plus m, so you get a square root decay and an exponential piece. Just speaking a little bit about what the physicists did is that in the magnificent tour de force, T.T. Wu actually did the same calculations which Michael had done, but did them accurately into a higher order and obtained explicit constants like this, and to higher order. So I just want to mention that point. So now we come to our second challenge, how to include these different kinds of singularity when you have winding. Also, when T is bigger than TC, you find your symbol will also have winding. So now, in addition to these new questions which are being raised in Topelitz theory by the Ising model, other kinds of singularities were also beginning to appear in a way which will influence what we do. And for example, in 1964, in his work on the ground state of the one-dimensional system of impenetrable bosons, Lenard expressed the one-particle density matrix for the system as a Toeplitz matrix with a symbol that vanished at some points on the circle. So this is a new kind of singularity. Before, we've either had symbols which are smooth and non-zero with no winding, or they don't vanish and they have some winding. Now a new type of phenomena is coming up. What happens if your symbol actually vanishes at a point in on the unit circle? So this was a new feature. Now, in 1968, with this in mind, and in a major step in the development and generalization of the strong Szegö limiter, Fisher-Hartwig introduced a class of symbols for Toplitz terms that allowed for zeros, singularities, discontinuities, and non-zero winding. So this is capturing all the type of difficulties which had arisen to that point. Now, symbols of Fisher-Hartwig type have the following form. Now this is, I would ask you to just focus on this. So this part over here is the kind of part that you have when your system is completely regular. So V, think of as being a smooth function because it's an exponential of something. It doesn't vanish and has zero winding as long as V is a smooth function on this. So this is the good part. Now we begin to introduce these singular. You fix your arguments, or you fix your roots, or whatever you want to call your branches, by always taking Z on the unit circle to be e to the I theta, where theta is between 0 and 2 pi. So wherever you see a Z, you put e to the I theta, where theta is a number between 0 and 2 pi. The ZJs are points on the unit circle, and there are m plus 1 of them. Always the first Z0 is at 0. Now G is a function which is takes on two values. It's so it's piecewise constant. It's e to the I pi of beta j and e to the minus I pi of j. This is for arg Z between 0 and theta j, and this part here is for arg Z bigger or equal to theta j and less than 2 pi. So on one part of the circle, it's e to the I pi j. So this has a jump, just a discontinuity. We have this quantity here, so that the real part is 2 times the real is bigger than minus 1, so it's an integrable singularity, and V is some smooth function. Now these different singularities capture these different features we spoke about. If you express Z in terms of e to the I theta and e to the I theta j, you see that this piece over here is giving you m plus 1 root type singularities, which allows for the possibility your symbol could vanish at some point. If you look at this combination here, so this is your piecewise constant function, you'll see that it is continuous at z equals 1, but it has a jump singularity at zj. So this allows both for winding and for jump singularities. This quantity is just to give you some bookkeeping. Now clearly, if all these alphas and betas are 0, you reduce to the regular case. So here are some examples. You've got a function f, which just takes on two values. It's minus I on the upper hemisphere and plus I on the lower. So jumped in discontinuity. So you find, and it can be written in Fisher-Hartwig form, where there is one singularity at z equals 1 and the strength is a half. A second singularity at minus 1, strength is minus a half, but there is no root type singularity. So here, this is what it looks like. Now suppose you've got a function which can take a nice smooth function, but it has zeros at 2 points. That can be written as now with a mixture of root type singularities and these windings or these discontinuities. And the reasons why I'm giving these examples, I'm not asking you to remember them, but just so that you see the kind of function which is coming up. I'm almost done, I think. Yeah. In Lenard's work on impenetrable bosons, this is the F he gets, which has the zeros at e to the I theta 1, and so that can be written where the betas are 0. There's no winding, but you've got these root type singularities. And then if you work out, and I won't write down, if you take the Ising model case, if you take phi Onsager, then you'll find that if you're at critical temperature, it can be written in this Fisher-Hartwig form. As for t, and also for t bigger than tc, but here you've got winding of, you've got beta 0 equals minus half, and for t bigger than t0, you've got beta z equals minus half. The message here is not the details, but you see that these notions of Fisher-Hartwig are general enough to include all these cases we've been talking about. So in tomorrow's talk, I'm going to begin saying is how you evaluate the determinants in these cases. Okay.
Can we assume that you will show some of this technical stuff once more tomorrow?
Absolutely. Okay.